Everyone, today I want to talk to you about why characterization is so important when we're studying materials. These materials are incredibly small and their properties often change compared to the bulk version of the same substance. So to really understand them, the science need to specialize tools, and I will introduce you four powerful techniques. The small angle X-ray scattering, X-ray absorption spectroscopy, electron tomography, and time of flight secondary ion mass spectroscopy. Each one tells us something different, and together I will give you a full picture. So let's start with small angle X-ray scattering. When X-ray pass through the solution with nanoparticles, they scatter at very small angles. By analyzing the patterns, scientists can figure out the average size and shape of particles and see if they are clustering. So what makes this method special is that it can be used during synthesis, letting us what particles growing, form and grow in real time. For example, when gold nanoparticles are made, these techniques show how they evolve, and when combined with the ultraviolet visible spectroscopy, it explains why the color and optical properties change. So the second method is the X-ray absorption spectroscopy. Instead of looking at overall size, this one focuses on the local environment atoms. It reveals details like oxidation states, bond length, and how many neighbors each atom has. The great advantage is that it works even if the nanoparticles are not perfectly crystalline. For example, studies of cadmium sulfate nanoparticles show that when the particles are very small, the bond between cadmium and sulfur atoms becomes shorter and the number of neighbors decreases. That proves how survey effects dominate a nanoscales. Now, let's talk about electron tomography. Regular electron microscopy gives us the flat two-dimensional images, but nanoparticles are three-dimensional objects, and a flat picture can be misleading. With tomography and the sample is sterile and many images are taken, which are then reconstructed into a full 3D model. This way can be see hollow interiors, layered structures, or defects that in a single image will hide. One study used the technique to show how large groups of nanoparticles form other structures, which help explain their optical and catalytic behavior. And finally, we have the time of flight secondary ion mass spectroscopy. This one looks at very surface nanoparticles. A beam of ions hits sample, knocking off fragments that are analyzed in a mass spectroscope. From this, we can get chemical fingerprints of the surface. It's so sensitive that it can detect coatings, ligands, or contaminants. A great example is the gold nanoparticle with T-glucose molecules attached. These techniques confirm the sugar fragments and show how they can bound to the metal surface. Crucial for information of biomedical uses, since surface chemistry controls how nanoparticles interact with cells. So, what do you use these four methods teach us? First, no single technique works for everything. Each has strengths and limitations, but when we combine them, we get both structure and chemistry. If only one look at shape and size, we will miss important details about bonding and surface ligands. If we only study chemistry, we will ignore morphology or porosity. Together, they provide a complete and reliable understanding. And yes, sometimes results may conflict. One technique might be the particles are 10 nanometers, another say 12. That usually happens because each method measures something different. The best solution is to repeat experiments, refine the analysis, or use another technique as a referee. To conclude, a characterization is not just an afterthought, it's just a foundation of nanoscience. A small group a small angle X-ray scattering shows particles grow, X-ray absorption spectroscopy uncovers local chemistry, electron tomography reconstructs the true 3D shape, and time of flight secondary ion mass spectroscopy reveals the surface. Each technique had a piece of puzzle, and only together do they explain why nanomaterials behave the way they do. So that's it for today, and thank you for your attention.